As you know quite well by now, there are two operations that you can do on vectors in Rn. You can add them, you can take two vectors and add them together, or you can take a vector and a scalar and you can do scalar multiplication times that vector. Think back on everything that we've done so far this semester. I'm going to try to convince you that these two operations are the fundamental operations in the subject, in the sense that everything that we've studied so far in this class originate with these two operations. For example, linear transformations are defined in terms of addition and scalar multiplication. They're defined as transformations which are compatible with these two operations in a certain way. And then from linear transformations, you get a lot of other things that we've studied, like matrices, linear systems of equations, and so on. The definition of subspace was in terms of addition and scalar multiplication. Look back at the definition, and you'll see. And then subspaces helped us to understand linear transformations better because we can interpret the kernel of a linear transformation and the image of a linear transformation as subspaces. Linear combinations of vectors are formed using addition and scalar multiplication. And then from that concept, you get the concept of span, which would be the set of all linear combinations of certain vectors, or linear independence, which has to do with when one vector can be written as a linear combination of the other vectors in the set. So, if you're willing to believe that this is true, that these two operations are the fundamental operations of linear algebra, then you might be ready to revisit this question of what is linear algebra? At the beginning of the semester, we probably would have said that linear algebra is the study of vectors in Rn and things like matrices and linear systems of equations. But really, linear algebra is the study of addition and scalar multiplication. Or to be a little more precise, it's the study of objects that have those operations. And anytime you have those operations, you can define linear transformations, subspaces, linear combinations. You don't have to be working just with vectors in Rn. And there actually are interesting objects that you've encountered before in math classes that have this property that they can be added and scalar multiplied. One example is functions. If you have a function f of x and another function g of x, you can add them together and get a new function. Or you can take a function and you can multiply it by a constant. You get a new function. Another example is matrices. You can add two matrices together as long as they're the same dimension. And you can multiply matrices by scalars. And so what we'd like to do is study linear algebra at this higher level where we're not just talking about vectors in Rn anymore, but we're talking about anything that fits this definition where you can add two things together and you can multiply by scalars. And the way to achieve this higher level of study is to use what's called an axiomatic approach. Basically, the idea with an axiomatic approach is that rather than saying what the thing is exactly, you say how it is. What does it do? And then anything that does the things that a vector space is supposed to do counts as a vector space. Okay, so here's the definition. A vector space is a set V that has operations of addition, which means that if you take two elements in the set, there's a rule for how to add those two elements together and get something else that's in the set. And scalar multiplication, which means that if you have an element of the set and a real number, then there's a rule for how to multiply those together and get another element of the set. And now an important point is that just like we're not actually saying what this set V is, we're also not actually saying what the addition and the scalar multiplication operations are. So we also need to specify that these operations satisfy the properties that we would expect addition and scalar multiplication to satisfy. These are all properties that you're familiar with, but we do actually have to list all of them as axioms for a vector space. So the first one is associativity of addition, that if you add u plus v and then add w, you get the same thing as if you added v plus w first and then added u. The second axiom is commutativity of addition. U plus v is equal to v plus u. The third axiom is the existence of a zero vector, which means that there's a special element of the set, which we call 0, which has the property that v plus 0 is equal to v for all v in the set. The fourth axiom is the existence of minuses. This says that for every v in the set, there is another element, minus v, such that when you add v plus minus v, you get 0. The fifth axiom is a distributivity law, which says that if you have k times u plus v, then that distributes as k times u plus k times v. The sixth axiom is another distributivity law, which says that if you have k plus l times v, that distributes as k times v plus l times v. We're not done yet. Almost there, but not done yet. The seventh axiom is a scalar associativity, which means that if you have two scalars, k and l, you can multiply k times l, and then scalar multiply times v, or you can scalar multiply by l, and then scalar multiply by k, and you should get the same thing. And then, the eighth and final axiom is that if you take any element in the set and scalar multiply by 1, then you get the same thing back. Okay, so this is a lot of axioms, and you don't have to memorize them. Don't worry about that. But the first thing to observe is that I don't think there's anything here that's particularly surprising. Like, these are the properties that you're already used to using when you do algebra. And that's why they're here. These axioms ensure that if we're working with a vector space, we can do algebra in the way that we're normally used to doing algebra, and everything will work exactly the way it's supposed to. So what you will be expected to do is to recognize and verify these axioms in a specific context, where you're given a set V with specific operations for addition and scalar multiplication. I'll show you some interesting examples of that later, but I'll point out that in the cases that you're most likely to encounter, such as functions and matrices, these axioms are very straightforward to check to the point where you might not even feel like you're doing anything important. All right, so let's look at some examples of vector spaces. Of course, the prototypical example is the one that we've been studying all semester long so far, which is Rn. I don't think there's anything more to say about that. So another example is a space of functions. In this case, f of RR is supposed to denote functions where the input can be any real number and the output is a real number. So for example, x squared, sine of x, and e to the x are all elements of f of RR. But 1 over x and ln of x are not in f of RR because they're not defined for all x. So you might think that's weird because those are functions that you're used to studying, but the point is that you have to be very careful when you're defining a vector space about saying what is and what isn't in the vector space. And the definition of FRR says that any real number should be a valid input for the function. And so that excludes 1 over x and ln of x. But there are other vector spaces that we could define that could include 1 over x and ln of x, and we'll talk about that in a second. Another important point is that this definition of FRR doesn't require the functions to be nice in any particular way. They just have to be defined. So they don't have to be differentiable, they don't have to be continuous, and that means it includes things like the absolute value of x and the floor function of x, which, in case you haven't seen it before, the floor function is just a function that rounds x down to the nearest integer. So for example, the floor of square root of x is 1, the floor of pi is 3, the floor of e is 2. It's just rounding down to the nearest integer. So the floor function is not continuous, but it's a valid function. It's defined for all x. Now, you're used to adding and scalar multiplying functions. You've been doing that ever since you started algebra back in high school. But it's worth thinking a little bit about how these things are actually defined. The idea is that when you add two functions together, if you have an f and a g and you calculate f plus g, that function is defined by the fact that f plus g of x is f of x plus g of x. The plus signs in this equation are actually different. The one on the left is the addition of functions, and the one on the right is the addition of real numbers. And what's going on here is that we're using the addition of real numbers to define the addition of functions. And so, for example, using this definition of addition, we can verify the associativity property. And it works like this. If we have three functions, f, g, and h, and we're calculating f plus g, parentheses, plus h, then we can unravel that expression using the addition rule. So the first step would be to write it as f plus g of x plus h of x, and then use the addition rule again to rewrite it as f of x plus g of x, parentheses, plus h of x. But now, this is an expression that involves addition of real numbers, and we already know that real numbers are associative. So we can rewrite that as f plus g of x plus h of x, parentheses, and then spool everything back up into a sum of functions. And when we do that, we get f plus parentheses g plus h of x. So the point here is that the associativity of functions actually came from the associativity of real numbers. That was the key step in the proof. But it's important that we were able to go through this verification. And if we really want to be complete, then we need to also define scalar multiplication of functions in a similar way and go through all 8 axioms. That would really take a long time to do, and so I'm not going to make you do all of them. I think you can trust that everything will work out okay, but I think you should be in a situation where you feel like you could, if I asked you to do one of them or two of them, that you'd be able to verify the axioms. And so actually there's a more general situation, which is f of SR, where S can be any set. It doesn't even have to be a set of numbers. It could be like the set of students in the class, or the set of all books that have ever been written, or the set of movies that are on Netflix. And you could study the vector space of functions that take elements of that set as input and produce real numbers as output. And what's kind of neat is that this verification of associativity that I did for f of r, it works exactly the same in this context, because I never actually said what x was in that verification proof. We never actually did anything with x in that proof. It was really just a placeholder for whatever the input variable was. But anyway, if you want to include 1 over x and ln of x in a set of functions, this gives you a way to do it. For example, you could use f of r plus r, where r plus is the set of positive real numbers. And then 1 over x and ln of x are defined on all positive real numbers, and so they are elements of f of r plus r. And then finally, one more example before I end. There's the set of n by m matrices. So you fix the n and the m, and then once you consider matrices of that fixed dimension, you can add them together, you can multiply them by a scalar, and it does satisfy the axioms of a vector space. I think it's worth you just sort of thinking through how exactly is the addition of matrices defined, how exactly is the scalar multiplication defined, and just going through and checking the axioms. In the end, the check of the axioms is kind of simple, maybe even like so simple that you might feel like, did I actually do anything? Did I really solve the problem? But if you look at the calculations carefully, you'll notice that at some point you're going to use properties of the real numbers, like the fact that real numbers are associative and commutative, and that the properties of matrices come from those properties of real numbers. All right, so we'll see some more examples later as we proceed a little further in the subject, but I'd say that these are actually the most important first examples, and everything else can almost come from these in a sense, but we'll talk about that later. All right.